Hi, my name's Tom Dick. I'm a mathematics professor and a math advisor for Texas Instruments. This video is part of the TI in Focus AP Calculus series, in which we'll look at the topic of particle motion in the coordinate plane using the TI-84. We'll consider in detail free response question 2 from the released AP BC exam for 2021. Here's a look at that problem. We're given a particle moving in the xy plane. We're given its velocity vector. And we're given an initial position, -2,5. We're asked to find the particle's speed and acceleration at time 1.2. Let's get started using the 84. First things first, we'll set our mode to parametric from function. And then we will return to the calculator screen and then to the y equals, where we're going to leave x1 and y1 for position functions. But we'll use x2 and y2 for those velocity components. So x2 of t, I'm going to enter the given x component of the velocity that was given in the problem. And that was the quantity t minus 1 times e raised to the t squared power. So we'll get that entered in for our x component of velocity. And now we can turn to the y-coordinate of the velocity. So y2 of t, will enter in here the sine of t raised to the 1.25 power. Now once we've entered the y component of the velocity, we can return to the calculator screen and answer the questions posed in part A of this problem. Now we were first asked what the speed of the particle is at time t equals 1.2. And for that I'll need to find the length of the velocity vector, which will be the square root of the sum of the squares of its components, evaluated at 1.2. So you see that square root symbol. I've retrieved x2 of t, evaluated at 1.2, raised that to the second power, and then we'll add. We'll do the same now for the y component. We'll retrieve y2t, that's the y component of our velocity, evaluate it at 1.2, and we'll square that value, and that sum of squares under the square root gives us the speed or magnitude of the velocity of 1.27148847 at time t equals 1.2. Now we're also asked for the acceleration vector. We're going to give that in two components, just like the velocity vector. We'll use x3 and y3 to take the derivatives of the x and y components of the velocity vector. So I've pulled up the derivative from the math menu, derivative with respect to t. And now I'll just retrieve x2 of t, and it's going to differentiate. This derivative is set up for a specific value, but if I just put in t, it'll give me the derivative function for the acceleration. And we'll do the same for the y component. So the y component of acceleration will be the derivative of the y component of the velocity. So I'll retrieve y2 of t, differentiate with respect to t, evaluate it at t, and there are our components of our acceleration function right here. If I return to the calculator screen, I can now evaluate those two components that I've just defined at 1.2 to answer that question about acceleration. So here's x3t. We'll evaluate it at 1.2. This will give us the x component of our acceleration. There it is. Now we'll do the same. We'll retrieve y3t from the parametric y variables menu. Go down, retrieve it, and evaluate that at 1.2. Now give us the y component of our acceleration. And there we go. So that's answered part A of this question. Let's turn to part B now. Part B of this question asks for the total distance traveled by the particle over the time interval 0 to 1.2. All right, So let's return to the 84. And for this, we'll need an integral. So I'll pull up the fn_int. It gives me a nice integral template. I'm going to integrate from 0 to 1.2. That's our time interval. And we're going to need to integrate a speed function, which would be the magnitude of velocity. Now, we took a lot of trouble to type in that speed value at the top. So what I've done is gone up and retrieved it. I'm just going to edit it by replacing the 1.2s, the specific value we used in part A, with t. So I'm entering a general speed function as my integrand by replacing 1.2 by t wherever it appeared. So there's our speed function for our integrand, and now we'll integrate with respect to t over the interval from 0 to 1.2. There's our nice setup, and now we just enter, and we get a value that represents the total distance traveled by the particle over that time interval. Now in part C, we're asked to find the coordinates of the point which particle is farthest to the left and explain why there is no such point where it's furthest to the right. Okay, now we've got that initial position of -2, 5 and a velocity vector. We're going to use that to create position functions for this particle. Alright, so when we go to the y equals menu, you will remember we left x1 and y1 blank for that purpose, so we'll have those spots for the position. So for x1t, I enter the initial x-coordinate at time 0, which was -2. I'm going to add on an integral that will represent the change in the x-coordinate over the time interval from 0 to t. So we'll integrate from 0 to t the x component of the velocity. So I'll need to go to y variables to pick off my parametric x component of velocity, which was x2. And then we'll just integrate that with respect to t, and that will give us the x-coordinate of our position at time t. For the y-coordinate, we'll need the initial y-coordinate at time 0, which is 5, and we'll add on the change, net change in the y-coordinate of the position by integrating the y-coordinate of the velocity over the time interval from 0 to t. So we'll integrate from 0 to t. I'll need to retrieve y2t from our parametric y variables menu. Let's do that. Scroll down, get to y2 of t, and then we'll integrate with respect to t, and that gives us coordinate position functions for our particle p. Now I'm turning off or deselecting x2, y2, x3, yt because I just want to graph the position of this particle. Now I'm just arbitrarily, starting at time t equals 0, I'll go ahead and graph this up till time t equal 2. The t step is 0.1. And you can see it just kind of stops there. That's because I just kind of arbitrarily chose 2. I think if I'd gone even to 2.1, it would have taken it off the screen. But there's our particle. And if we trace, you can actually see the cursor moving along. As the trace is nice for kind of visualizing the motion of the particle. And it looked like at t equal 1, it seems like we're about as far to the left as we could go, because then it seems to be turning around and moving to the right. Now the question is that point at t equal 1, is that the leftmost point this particle for all time reaches? And does it just kind of keep going forever to the right? What's going on with that? For that we'll need a little bit deeper analysis. So we're going to return to the y equals menu and take a look at our velocity function very carefully. So the x component, if we're looking at left and right, we're talking about the x-coordinate. And notice we've got that factor of t minus 1 and a factor of e to the t squared. Now t minus 1 will be negative when t has a value less than 1, and it will be positive when t has a value greater than 1. The e to the t squared will always be positive. So indeed, the x-coordinate or x-component of velocity is exactly 0 at 1, and that will represent the leftmost point of our position of our particle. So I'm going to evaluate x1t at 1 to get the x-coordinate of the position. And if we want the y-coordinate, we'll need to retrieve that. So now we get the y1t at t equals 1. Once we calculate y1t of 1, we have the coordinates of our leftmost position. Well, that winds up this video. For more resources like these, go to education.ti.com.